Alrighty, on to lesson number, what are we on? Lesson number 2 in calculus. So in our first lesson, we talked about the average rate of change. And again, that's just telling you like what the other way of thinking of that is the average slope over an interval from like A to B. And we use 2 points to find that average rate of change. Okay. Now, the idea that we talked about yesterday is that we want that interval to get smaller and smaller and smaller, so much so until it's to 1 point, to when we're finding that instantaneous rate of change, the rate of change at 1 point on a curve. Okay. So right now, all we know how to do is find the average velocity. And here in this question for warm up, we're practicing finding that, right? So we're going to use smaller and smaller and smaller intervals to help us estimate the instantaneous rate of change or instantaneous velocity at a particular point. So try this problem on your own. Don't let the equation scare you here. V of 0 and h of 0 are given in the problem, right? Here's V of 0, that's your initial velocity, and here's your initial height. I should actually say meters. Okay, so try that problem and we'll go over it in class together. Okay, but it's a good practice of yesterday's notes. All right, today's lesson is on limits, and limits were taught in pre-cal, so it might be a little bit of a review to you, but for some of y'all it might not be, so that's okay. Either way, let's kind of refresh ourselves on what a limit is and why we're learning it today. Okay, first of all, the notation how it's written is you'd say the limit of f of x as x is approaching some a value, some constant. And the idea is that's going to equal some value, some limit. Okay. Now, the limit value, L, whatever we get when we take the limit, is a number that you can get extremely close to from the left and the right without necessarily equaling that number. Okay? So, the idea that we talked about yesterday, that instantaneous rate of change that we're trying to build up to, comes from limits. Okay, so an instantaneous rate of change by definition is going to involve limits, so we need to understand that. And as we learn more about limits and the rate of change, you're going to see how those two kind of work together. Okay, but for right now, it's really important that we understand what a limit value is. So it's a value that we get really, really close to, but not necessarily have to equal. All right, so let me show you some examples on a graph. Now, if you have just a regular continuous graph, like a quadratic or cubic or something that's just, a continuous motion, the limit value as we approach left to right, left or right, it's nothing exciting about that, okay? So the limit is just going to be equal to the value. So let's look at like other types of possible like different limits that you might run into. All right, let's talk about removable first. Removable discontinuity. So limits are particularly interesting when we're talking about discontinuous graphs, right? So let me draw you an example. Let's say this is at 1, and we'll just call this value, it looks like it's A, okay? So let's say that we have a graph that's coming, and then it's an open circle at A. We'll say that happens at 1/2, okay? And then the graph goes on. So there tends to be a hole at A. But let's say that point A is defined right here at 1, okay? So we have a graph that isn't continuous. There seems to be a hole at that continuous portion, but it's defined at A. So the limit in this case, all right, of f of x, as x is approaching A, is equal to that number that it's getting really, really close to, but not necessarily touching from the left and right. So from the left, we're coming right here. From the right, we're coming right here. So you see it's getting really, really close to the value 1/2, even though that's not the value of the function, that's not defined there. It's getting really, really close to it, but not touching it. Which is different than me saying like, hey, what is just plain old f of a. F of a is defined at the point 1, right? You can see the closed circle, that's the value that's actually defined, which is not necessarily equal to the limit. So that's just an interesting thing about limits is the value that's getting really close to, but not necessarily have to be equal. So that's removable discontinuity. Another one is point discontinuity. Discontinuity. And that's going to look very similar to A, but instead of having that dot, it's just going to be a hole. All right. So for instance, we'll say this is 1 again. This is A. The graph would look something like, I don't know, this. Okay. And if you notice, it looks very similar to A. It's just now that at point A, it's not defined. So the limit, we'll say in this case, the limit of f of x as x is approaching A is actually still equal to 1, okay? Because that's what's approaching from the left and from the right. It's approaching this hole right here. It still may not have a value. The only difference from part A is that that f of A, no longer exists because there is no value there. So that's another type of interesting limit there. Let's get another one here. Let's see. How about, you're probably familiar with this one a lot from piecewise functions, jump discontinuity. Alright, so I'll give you an example of that. Let's say we're here at 1 again, this is A. Let's bring back 1/2. Let's say that the function is defined right here at 1, and it goes off like that, but it jumps to another value as we go to the right. Okay. So notice right here at A, f of A is equal to 1 because that's the whole value, that's the closed circle, that's what it equals. But if I were to say that the limit, if I were to ask you for the limit of A, and say the limit as x is approaching A of f of x, what will that equal? Well, if you look from the right, we get to the value 1/2, and from the left, we get to the value 1. So since they don't match up, since they don't both meet that same point from the left and right, we would say that that limit does not exist, and we'll discuss that further. But in order for like the general limit, we call that, to exist, they have to be meeting from the left and the right. They have to be getting really close to that certain value. And the last one we're going to talk about is just kind of the generic example that you're used to seeing with functions, and that's just continuous. There is no discontinuity. And those are boring. We've dealt with those so many times. That would be like that function there. It's just a nice fluid continuous function. F of A just equals 1. And because we're coming from the left and right and meeting at that same point, then the limit also equals 1. So the limit of f of x as x is approaching A equals 1. So nothing too crazy about that, but there you go. Now, just a couple things about the limit. Whenever I say the limit, whenever I give you this notation right here, remember how it's read is the limit of f of x as x approaches A equals L. I sometimes say the limit as x approaches A of f of x. Sometimes I flip-flop these two, and it's not the biggest deal in the world, but that's how it's supposed to be read. L is a numerical limit. All right? If you actually are able to find the limit, it's going to be a number. And again, we are concerned with the values of x that approach A, not necessarily has to be the exact value of A, and we saw that in a few examples up above. Okay? Now, we talked about the generic limit from left and right, but we can also discuss it from different directions. We can talk about the right limit and the left limit. Let's show how that looks. So if I said right limit, I'm saying the limit of f of x as x is approaching A, and then we put a little plus symbol to signify that it's coming from the right. Okay, so we're not even worried about the left side. I'm just curious about what happens as I'm coming from the right side, what value am I approaching? Okay, and that could equal some number L. And the limit from the left will be the limit as x is approaching a. We put a little negative symbol there to signify that's coming from the left of f of x. And I'm curious what that would equal. Now, the general limit is what we were talking about above with all those examples. That's just saying generically the limit as x is approaching a, or let's see, I said it again backwards, of f of x equals a number. Now, this, by definition, a general limit is only true if the left and right limits are equal. So this exists if and only if, IFF means if and only if, and it means that it has to go both ways. Exists if and only if the limit of f of x as x is approaching a from the left equals the limit of f of x as x is approaching a from the right. Okay, so if those two limits match up, I mean, here's an example. Like a limit coming from the right. Let's say I want to know coming from the right from 1. So here's a function coming from the right, and that limit equaling some value. Here's a limit coming from the left and equaling some value. And as long as those two values equal the same exact value for the left and right, then the generic limit exists. I think that logically makes sense, right? If the left limit and the right limit are the same, then the generic limit exists, okay? Because they're meeting up at the same point. So just kind of keep that. All right, so I got a couple more examples I'd like to do with you. So we kind of talked about looking at a graph. Well, let's look at an equation that maybe follows one of those types of discontinuities, and then see and kind of discuss what that limit would be. Okay. So it says use your calculator. If you've got a graphing calculator, it'll be awesome if you could graph this in your calculator. If not, no big deal. And it's x cubed minus 1 over x minus 1, where x can obviously not equal 1 because it would make the denominator equal 0. So what you'll expect to happen at x equals 1 is that it's not going to exist, right? And there's going to be some type of issue at that point. Okay. Well, if you did happen to graph it, okay, you're going to notice that it's going to be some actually like quadratic looking function. And on your graphing calculator, it's probably going to look like that. But if you go over and try to, over the point 1 in the graphing calculator and try to identify the value there, you're going to see it doesn't exist. You're going to see just a hole there. So your calculator doesn't show holes very well, but rest assured there is a hole right there, meaning that there's no value defined there. Okay? It's not an asymptote, but it's a hole. Just do a little quick review of what that means. If I was given this function here, okay, and you graphed it, well, it looks like that. That's good. But how did that work out? Why does it work that way? Okay. Well, we're smart little kids. We know how to factor, and even though I did mess this up in one of the classes, just a reminder that how I factor this, that's a difference of cubes, and I might have misspoke in one of my classes on that. But how that factors is like if you have a squared or a cubed minus b cubed, that actually factors to a minus b times a squared plus, and it's not 2ab, I was mixing those up by accident, it's just ab and then plus b squared. Okay. So if I would actually factor to the top of this function, it would be x minus 1 times x squared plus x times 1 is x, and then plus b squared is 1, all over x minus 1. So you're going to notice that the denominator actually cancels out. And what you may remember from rationals way back when is that whenever you cancel out like a value that doesn't exist, something that's like on the bottom of a rational, that value is actually a hole that you're canceling out. See, the value that doesn't exist is either a vertical asymptote or a hole. If it doesn't cancel out, it's a vertical asymptote. But if the factor does cancel out, it's a hole. So really what you're graphing on your calculator is this quadratic just with a hole at 1. So that's kind of where that shape comes from. Okay? But let's pretend like we didn't know how that works. Let's pretend like we didn't know that was going to be a hole and we didn't know how to factor. Let's pretend like we're just investigating the behavior of f as x is approaching 1 from the left and 1 from the right. So we know that the limit is going to exist because they're converging at the same point from the left and right. But let's pretend like we didn't know that. Okay? So in your calculator, we were going to investigate a little bit. We were going to, with using the function f of x equals x cubed minus 1 over x minus 1, we were going to plug each of these values into the calculator. I usually have half the class to the left side and usually have half the class to the right side. But take a minute, maybe pause the video, check my work on this, plug each of those values into the function, and we'll investigate kind of what's going on. And I'm going to go ahead and kind of fill those out for you right now. I'm getting 2.3125, 2.71, 2.9701, 2.997. You notice as I'm coming from the left, it's going 2.3, 2.7, 2.9, 2.99. It's getting obviously closer and closer to 3, which we know that if we were to plug 1 into the simplified version, right? Same way backwards here. 3.8125, 3.31, 3.0301, 3.003. You notice that it's going from a high 3 all the way down to low 3. You notice that these are getting closer and closer to the value 3. Okay. So f of x is approaching 3. From this information, we can estimate that the limit as f of x as x approaches 1 is indeed 3. Now, this right here, this was nothing more than just a little investigation tool to kind of show you how a limit works. It's getting closer and closer to the same value from the left and right. But this is going to be very unreasonable. We don't want to be doing this, especially if we don't have a calculator. We don't want to be testing points to figure it out. Obviously, it is a good last resort. But what we're going to learn is little factoring tricks and stuff like above here to where we can identify the hole and then figure out what value it's approaching from the left and right. So, nice little investigating tool into limits. All right, I just got a couple more for you here. Okay, it says sample 2. So, hint, think of the limit as the height of the graph of the function is trying to reach. So, it's the value you're trying to reach, but not necessarily equaling. Okay? All right, I think these next few examples are some good ones to consider. It says, find the limit of f of x as x is approaching 0, where f is defined as blah. So if you remember correctly, this is actually a piecewise function. Okay, I want to know what's happening as I'm approaching 0 when given this piecewise function. So remember that a piecewise function is graphed in pieces. So let's look at this graphically and then identify what's going on at 0. Okay. All right. So it says that whenever x is less than 0, we're at the value 1. And whenever x is greater than or equal to 0, we're at the value 0. So how that looks is, at 0, the value is 0. And any x value to the right of that is also 0. So that's like at 1, 2, 3, 4, it's always going to be 0. It's just a linear equation. And then for any value less than 0, so that's starting at 0 but not equaling it, anything less than that, so like -1, -2, -3, the value is always going to be equal to 1. So that's what a piecewise function looks like. Okay. Now, if I were to ask you what is f of 0, you just say 0 because that's where the closed circle's at. Okay. Let's think about the limit. Let's think about it in terms of left and right limit. If I were to say the limit of f of x as x is approaching a from, say, the left. All right, well, here it's coming in from the left. That value is equal to 1. What about the limit of f of x as x is approaching a from the right? Well, as I come in from the right-hand side, that value is going to equal 0. And those two values do not equal. You can clearly see that from the graph, that the limit, as I'm approaching f of x at 0, obviously does not exist because they do not match up at the same point. Okay, so there you go. The next one's actually a pretty interesting one. Find the limit if it exists. This is the absolute value of x divided by x, and we're trying to find the limit at 0. All right, well, um, kind of an interesting little problem here. Let's kind of discuss it in terms of absolute value real quick, what that means. By definition, like you know what the absolute value graph looks like. It looks like this, right? And if you didn't realize it, all absolute value is just two separate equations. It's the equation y equals x and the equation y equals negative x, and they converge at the point 0, right? Did you know that by definition, um, absolute value of x actually equals the function x whenever x is greater than 0, and negative x whenever x is less than or equal to 0. And those inequalities can be the same because, I mean, they can both be included or vice versa, whatever. But that creates this graph right here, right? So you can think of this again as a piecewise function, just like we did in part A. Like if I were to graph what's going on here, whenever x is greater than or equal to 0, it's positive x divided by x, which is positive 1. So you could say something like along the lines of um, like this right here. And then whenever x is say um, less than 0, the top part's actually negative, right? So then it's going to be -1 for your value. It's going to look like this. I mean, test the point. Like if I were to plug in, say like -2, that's going to be the absolute value of -2 over -2, which is -1. Okay, so I mean it's x divided by x, which is great, which usually is just going to be +1. But because of that absolute value symbol, if I were to plug in a negative x, that could be -1, right? So that's actually the graph of this function here. So what happens, and the reason that they're both open circles is because you can't divide by 0, so the point's undefined there. And what's interesting, if I'm approaching x to 0, again, same argument as before, the left and right limits do not match up, so therefore this does not exist. Okay. And then lastly, discuss the existence of the limit of 1 over x squared as x approaches 0. If you would actually graph this, like right here, this is a vertical asymptote. X equals 0 is a vertical asymptote because if I plug 0 into that, it makes the function undefined. So you're going to see this vertical asymptote here, and that since that doesn't cross out, it's not a hole, it's going to be a vertical asymptote. But if you were to test points or graph this in your calculator, the function looks like this. So let's discuss how that works here. Let's discuss the general limit here in terms of left and right limit. Like if I were to say the limit of f of x as x is approaching 0 from the right, like so as I'm coming in from the right side, all right, what's happening? Let's go on to positive infinity, all right? It's just going up and up and up forever. Well, what happens if I go and ask for the limit from 0 from the left side, so as I come in from the left? Well, again, that's going to positive infinity. And since those values are equal, then the generic limit is also equal to infinity. All right? So that's how limits work. Okay, if the left and right limit are equal, then the generic limit equals. Since they both are going to infinity, the limit is actually equal to infinity. Right. So there's a little bit of a lesson on limits. I would like for you to try this problem on your own. This is the function 1 over x. See if you can get these limits. You got a left and right limit, some generic limits, and then D and E are doing limits to infinity. And you've seen limits to infinity before. That's how x is going either to the right for positive infinity or to the left for negative infinity. And you've seen that before as in behavior. In behavior. Which is kind of what I got right here. Just to give you some quick examples real quick. So let's say that A is actually a vertical asymptote. And let's just say that that's the end of a function here. Like, let's just assume that the right side is also converging. I mean, if you want to draw this to make this problem a little bit more applicable, you can. But by definition, it says as limit is approaching A, and you can even say, if we want to say from the right, we can, or I'm sorry, from the left, if that even makes it better, whatever. That's actually equal to negative infinity. That's the definition. For vertical asymptotes. Okay, we would say that the limit as x is approaching a of f of x would equal plus or minus infinity. And that could be from both sides, that could be from just the left, that could be just from the right. Okay, no matter what, if your limit ever equals plus or minus infinity, that is by definition a vertical asymptote. Okay, so if your output of a limit, let me say that again, if your output of a limit is a infinity or positive infinity, that means at that value a is a vertical asymptote. And by similar argument here, we could say like the reverse. If we're taking the limit to infinity, then that's in behavior. Okay, this is called a definition of horizontal asymptote. So like if the limit as we go to infinity equals some number, it's not infinity or positive infinity, then that number is by definition a horizontal asymptote. So if I take the limit as x is approaching infinity, either to positive or negative infinity, doesn't matter, plus or minus infinity of f of x, if that equals any number, by definition, that is a horizontal asymptote. So in this case right here, it would be a. So that'll help you with the last slide as well. So try that last slide, and you can either try the homework already if you want to, but we're going to go over this tomorrow. And I'm trying to keep it under 30 minutes, and I did. So yay! Hopefully these videos are getting a little bit better. I'm getting more in the swing of things, trying to get back into the routine of videoing. So bear with me, we'll get there. And then there's, also you can try this problem too. So we'll go over this problem and the one before. Try these limits, see if you can get it. And that'll be kind of our lesson for tomorrow. There's your homework if you want to try these. I'm going to post a picture of these as well. So good job, guys.